Hi, this is a video about looking at COVID-19 epidemiological curves. I'm making this in April 19th, year 2020. I've made a little website. You can see it at the top here. The local is /Kelly, Kelley /COVID-19. On this, I have many different countries. You can see the list of countries here, and I'm from Canada, so I'm going to show you the Canada view next. The graphs here show 4 panels. The top left is the cumulative case count as a function of time. Black and gray dots are confirmed cases. Red and pink dots are deaths. And I've highlighted in darker colors the last 14 days. Over to the right here, that's just a log graph of the same. The log graph is quite useful because if the data are going on a straight line here, it means it's an exponential growth. And what I do is I compute, for each of these data sets, I compute the doubling time from the slope of that curve. It's related to the slope of the curve, it's not the slope of the curve. Down on the bottom left, this is the case count, and again, the highlighted dots are the recent ones, and the gray dots are the ones before that. The magenta line is just a fitting spline, it's a smoothing spline. I do this in R, all of this is done in R. There's no theory behind this spline. I'm not suggesting it means anything in particular, it's just to guide your eye. Over here on the right is the same thing as to its left, but now it's on a log scale. I live in Nova Scotia, so I also have cases by province, and I'm showing them here. Scrolling this very quickly because I want to get to the daily change. So this is the graph of the daily change there. This is Canada as a whole, the top left, Alberta. These are provinces or subregions within Canada. I live in Nova Scotia here. And you can see that the case count is increasing in Nova Scotia. And it appears that in Manitoba, which is to the west of us, that it had increased and now is decreasing. These tick marks correspond to a week. British Columbia, which is on the west coast, the case counts had a peak there. It looks like where my mouse is, and it really appears to me that it's decreasing. They're past their peak in cases. This is cases, it's not deaths that I'm looking at, it's cases. Newfoundland and Labrador to our east. So there are 3 that really stand out here, Nova Scotia, for not having a peak. I guess Alberta is another one. When I say 3, I guess I mean 4. But I want to focus a little bit on Nova Scotia. The question is, when you look at this, does it look like it's making a peak to you? That's really the question. And I'm going to show you a little bit of how you could try to figure that out, not based on anything fancy, just based on curve fitting. So this is a simulation here, which I'm doing in R. It's a Shawnee project. And I'm showing you here 2 panels. These are made up data. And what I did was I took a Gaussian curve and added some noise to it. That's the lower panel here. That's the case count. And then I did a cumulative sum of that. So I'm simulating here roughly what the data look like. I'm not saying that the real data form this curve or any other curve necessarily. Obviously, the way it will work is that eventually you'll asymptote to some number here when the epidemic is over. It starts at 0, gets up to some number. That number is the total number of cases that will have existed by the time the epidemic is over. Fine. And now this top thing is a slider, and you can move it back and forth. So I'm moving it to the left, and this is the observation days. So see that the blue line in the curves below moves as I do that. And you'll see another notation, and that is that for points that are before the so-called observation day, they're shown in highlighted in black, and they're in gray after. And you'll see here this label that says that there's insufficient data to make a prediction. What I'm doing here is I'm taking these data, not these data, I'm taking these data and I'm fitting a particular form to them. It turns out to be a hyperbolic tangent. That's actually not the integral of the shape, but I don't know what the shape is. I said a Gaussian, it could be almost anything. It could be a sesh squared, hyperbolic secant squared. And I'm not going into epidemiological theory here. honestly, we don't know the coefficients for it. So I don't think that the functional forms that derive from constant coefficients make any sense when we're doing social distancing and so forth. My only question is about building intuition. So I'm going to slide this slider over to the right a little bit. And it's still saying that there's insufficient data to make a prediction. And I think it should be pretty obvious to you. If you were looking at this cumulative case count, it's still, of course, going up. It can only go up because it's cumulative. And this daily case count is, just imagine that you don't see the data. This is the future, which you don't see, and this is the present. The blue is present. This is the past. I don't really think you would look at that and say, I think there's a peak. And the curve fitting algorithm is not finding a peak. Now, I'm on day 74, and I'm going to stop using the mouse, and I'm going to use the arrow key, and I'm going to click it forward one day. 75, and just focus on the bottom panel and ask yourself, would you, if you saw those data, would you think that you were seeing, that you were in the peak yet? I would probably say no. One more day. I might still say no, but at this point, this model converged. And now it may be actually converging for future points. We'll see that in a second. But now I want to direct your attention over here to the right. So this would suggest the data so far as of day 76 in this made-up scenario. This would suggest that you can fit a model. That fit, which is extended here with the red line, is really not a very good approximation of the data here. Looks like it's about 40,000, and the data, fake data, would be 50,000. So let me go forward another day. Getting a little closer, then a little closer. Seems like we're fitting better and better. Better still. Still better. Honestly, if I put enough noise in here, you would see sometimes that it would go above, that the red line would go above these data. These data are not actually as noisy, I think, as the real data. Now here, by the way, I think Canada is at the moment sort of in here. I mean, if I were to look at these data, they kind of look suggestive of falling. Go a little bit further. Maybe I'm going to go into what looks visually as though the data are falling. To me, in the bottom panel, it looks as though the data really are starting to fall. And at this point, well, we're doing a pretty good job. This model is fitting pretty well to the actual solution. Slide it more quickly up, and of course it's converged very well at this stage. And the point of this is that even here, and again these are for made-up data, even here, the data themselves can make a kind of a reasonable prediction of the final final case count, not death count, final case count. However, when you're in this kind of a situation, this model, yes, it can fit it. I'm using random noise. If I change to random noise, it might not quite fit it here, actually. So it's almost like it can do, to me, this is almost feels like, I think I would say that it's turning over. So the point is, this is why jurisdictions have this idea that they ought to wait about 2 weeks. They ought to have about 2 weeks of decreasing case counts. And that would be probably based on a 7-day smoothing average. So you can sort of see visually, I could have put more text, but you can probably see visually that moving the mouse here back and forth about 1 week, perhaps that's decreasing. I think they want to have a 2-week decreasing. Perhaps when we're here, that's what that would be. Right, so what have we got from this? When you're in the uptick phase, these data are poorly constraining this fit. You really can't tell when the peak will be or what the peak will be when it's still going up, unless you have some other way of knowing that. The data themselves won't really tell that to you. And this is what would be called a Monte Carlo experiment with made up, random numbers. It's very easy to do this. This is maybe 80 lines of code, which I could send to anyone who wanted it. dan.kelly@dell.ca. That's it for me. Stay home, stay safe,